Hello student, welcome to Power Electronics. Today, inshallah, we will go through lecture number 3 and inshallah we will see the uncontrolled rectifier, which is single phase full wave uncontrolled rectifier, which is in chapter number 4. You can go through sections 4.1 and 4.2 plus the handouts. Now, in single phase full wave rectifier, we have taken for the last week the half wave rectifier, uncontrolled rectifier, and we used one diode for our circuit. Now, inshallah, for this lecture, we will take four diodes as a bridge rectifier, okay, and we will see the output of the full wave uncontrolled rectifier, and we will see that we have better output voltage and better output current, and of course it will result with better output power. Okay, so we are going to outline introduction, and then we are going to use a bridge rectifier, and we'll see the output. We will go through the waveforms and how to draw them. Okay, after that we will see the center tap. We will use a center tap transformer in order to rectify the circuit. So this is a special connection with the transformer, and we'll use two diodes, and this way is representing two single phase half wave rectifiers together. Okay, we will see the advantage and also the disadvantages of such methods, and then at the end of this lecture we will go through example. Now, as you know, full wave rectifier, it is to produce an AC to convert from AC into DC component. Now, for a voltage or current, we need them to be converted to DC component, and the full wave rectifier is basically, as you can see here, basically is the same as the half wave rectifier, but it has advantages, and inshallah we will see the advantages here. Okay, now the output of the transformer is less ripple than the half wave rectifier, of course, and we will see with the waveform inshallah in the coming slides. This is just to give you introduction, and in this chapter, chapter number 4, uncontrolled and controlled single phase and three phase full wave converters we'll use as rectifiers. We will see them, and inshallah we are going to analyze everything step by step. Now we are going for the uncontrolled rectifier. Okay, full wave uncontrolled rectifier. Now 99% of the use of they are using a bridge rectifier. Okay, now the advantages is more aging factor, so it lasts more than the half wave rectifiers. Less power losses, of course we have less power losses, and the output power is more than the half wave rectifier. I think you have done this in the lab. You're supposed to finish the full wave rectifier in the lab, and you found that the full wave rectifier is almost the same as the input voltage. So the output voltage of the full wave rectifier is almost the same as the input voltage. Of course, there is a little bit of difference because of the small losses during the operation of converting from AC into DC. If we have less power losses, of course the efficiency is going to be more, and the disadvantages for this full wave rectifier is high cost. Now, why high cost? Because we have four rectifiers. We have four diodes. Okay, then in half wave rectifier we have only one diode. Here we have 4 diodes, so it is high cost. Okay, so it is more expensive than the half-wave rectifier. Now let us see the bridge rectifier here. Please follow the pointer here. This is a single phase full wave rectifier, and this is a bridge rectifier. Okay, now as you can see, we have D1 diode number 1, we have diode number 2, and we have diode number 3, and we have diode number 4. Now this is our supply. So see here, Vs, can you see? Okay, so this is our supply input voltage. Of course, the supply voltage is going to be AC, right? So this is AC, so it starts from here and it will go to the negative. This is one cycle, right? And the second cycle starts from here and it will go to the negative and stops at 2 pi, okay? For so each cycle starts from 0 and into 2 pi, okay? Now, of course, the current will be the same as the voltage for the source current, right? And it should have the same peak, okay? The same peak, but the same peak position, but not the same value, of course. It will be half of the voltage, almost half of the voltage, okay? So it will start from 0 and end in 2 pi, okay? Of course, positive and negative portions, because this is AC. Now, let us analyze this circuit and let us see how the current is going to pass through the diodes going to the load. This is our load. This is our rectification circuit, which is bridge rectifier, okay? And this is our supply voltage. We are going to convert from AC supply into through the rectification circuit into a DC supply, which is here. This is our output voltage. Here we have output voltage across the load, okay? Now in this case we have only resistive load. Now let me just point out something here very important. Now in case he said at the positive side of the power supply, so this is our positive. So in the time of this positive cycle, okay, let us see how the current moves. Now in the positive cycle we are going to use the red one, okay? Now this is our positive from the supply. It will go through this diode, right? Why is that? Because this diode here is a forward bias, of course, because the anode is positive and the supply is positive. So the diode here is acting like a wire, okay? So it will allow the current to move through this side. Now, of course, the current will not go through this side because this one is cathode, right? And D4 is acting like open circuit. So the current will not go through here. The current will go through diode 1. Now, after that, the current is going to be this side. And of course, it cannot go to D3 because, again, it is open circuit here. The diode is reverse bias, okay, and acts like open circuit. Now the current is going through the load, right? This is our load. We can say this is our load, okay. Then it will go from here, okay. Some of the students say that, why teacher, it does not go through D4? Of course, it cannot go here, okay? Because this wire is already positive, is already charged with positive, right? So, of course, it will not return from the same point. Of course, it needs to go to the negative, which is the supply here, okay? Now, of course, the current will go through this side, okay? So because of the D2 is forward bias, okay, and it will return to the supply. It will return to the supply. Now this is during only what? the positive circle. So the voltage, once we have a conduction of the diode, okay, then we have what يا شباب? We have, if we have if the diode is acting like a wire يا شباب, then there is no voltage, of course, because we don't have potential difference. The potential difference is zero, right? So for V diode 1 and V diode 2, the potential difference in this part, because it is acting like, so if you have a wire, okay, and you connect voltmeter here, now how much the voltage? Of course the voltage is zero because there is no potential difference, okay? That's why we have here 0 until 180, okay, until 180. Now this is for the first half cycle, which is the positive portion, okay, of the waveform. Now let me just erase, okay, and then I will show you the negative portion of our supply, okay. So in the positive sequence, in the positive peak, in the positive peak, which is positive sequence, the D1 and D2 conducts, of course, because they are forward bias, and D3 and D4 are not conducting, so they are reverse bias. Now, if it is conducting, it means that we have current, right? So this is the current, and we can draw the current for D1, D2 is this current. So this is already the supply current, okay? Now for the negative portion, we can take another circuit here. Let's go to this circuit. This is at the negative supply, okay, a negative supply waveform. This is our negative supply, right? Now in case of negative, the positive is finished, right يا شباب? So it is through D1 and D2. Now for the negative supply here, it is the same circuit. We have, this is our load, right? This is our supply here, and this is again the same rectification circuit, but now the our supply now is going for the negative portion, okay. This is the one. Now let us see how the circuit is behaving, okay. Now for the negative side here يا شباب, the current is going from this side, right? Okay, and through this diode, okay. So it cannot go down, it will go up, because down here D2 is reverse bias, so it will go from here. Of course it cannot go back here because this one also is reverse bias, so it will go from here, okay. It will go through the load, and it will come back here through D4, and it will return to the supply. Now why does not the current go for D2? Because and this wire is now charged with the positive, with the with the positive charge, and then it cannot go through here. Of course it is going to be returned to the supply, so it will take this path in order to return to the supply, right? So this is how it is working. And of course for the voltage here, if the D3 and D4 are conducting, so the voltage of course is zero. So this is our voltage here, so it is zero now. And also if they are conducting, so the current will be like this. Now we can combine those together inshallah in the coming slide, but let me explain something here very important. D3 and D4 are conducting forward bias, and D1 and D2 not conducting reverse bias. Now if they are conducting, as we said, we consider the voltage for the diode voltage is 0, right? Of course, what is the left of the AC wave is this one. So this we can draw. This is the for the diode, okay? Because this is what is left from the supply. You will understand inshallah in the coming slide. Now, this is as you can see here our circuit, okay? The same circuit. We have AC supply here. We have D1, D2, D3, D4, and we have here our load. Our load and the V out here should be in DC, right? Now, the operation is already discussed in the previous slides, but now, shabab, let us see what happens exactly. So from 0 up to pi, we have D1 and D2 working, right? So we have the positive cycle here. Now, for the negative portion of the supply, this is Vs, huh? This is Vs. For the negative portion of the supply, D3 and D4 is working, okay? And it will rectify this negative portion into positive. So it will be like this. This is sorry. Sorry guys, this is already positive, okay? So the diode will not rectify the circuit here, this waveform, and this is now D4. The supply is going through D3 and D4, so it is going to rectify the circuit here. So this is our peak. We can draw like this, and it will be like this. This is for the output. This is for one cycle. So this is our cycle, as you can see here. This is our positive voltage for the source, and this is the negative portion for the source, right? This is one cycle, as we said, and this is our other the second cycle, sorry. Okay. Now again, this is the same thing for the current. Of course, it will be the same as the voltage supply, but the peak is less. Okay. Now, this is our positive. Here, we say that the positive peak, as positive peak of the supply, we have D1 and D2. This is D1 and D2, right? We can write here D1 and D2. For the negative supply, negative peak supply, D3 and D4 is working, so it will be here to rectify the circuit. Okay, this is for cycle number 1. It is the same as the cycle number 2 here. Okay, here D1, D2, here D3 and D4, and so on. Okay, the current, of course, will be the same as the voltage for the output current, but the peak is less. Of course, it will be half of the voltage supply, voltage output, and we can conclude something very important. Let me just erase here a little bit, and then we can discuss those four factors. Now, here, shabab, he said that the phase shift between D1 and D3 is pi. Now let us check. Now this is D1. Here is D1, right? Here is D3. Okay. Now what is the phase shift? The D1 is started from 0. D3 and D4 started from pi. So the phase shift between them is pi. Okay. For D1 and D4, of course, the same as before. So this is D1 started from 0. D4 started from from pi, so the difference between them, the phase shift is pi. Now, what is the phase shift between D1, D2? No, there is no phase shift, it is zero. Why is that? Because D1 and D2 are conducting from the first positive peak, okay, from zero. They are conducting from the same at the same time, okay? Remember, this one was red and this one is red at the same time, okay? So it will conduct, the current will go from here, okay, through the load and come back to D2 and it will return to the supply. So there is no phase shift between D1 and D2, and of course diode 3, diode 4, there is no shift between them because both of them started from pi and ends at 2 pi, so there is no phase shift. Okay. Now this is for the full wave bridge and controlled rectifier. So this is our output voltage. Okay. Now, in this slide, we can see here, ya shabab, this is very important. This is very important. Let me just explain to you these formulas. Now, these formulas are for the full wave uncontrolled rectifier. Now, if we want to calculate V out DC, so it is 2 V maximum over pi, okay? And I out DC is V out DC divided by R, which is Ohm's law, right? Power also is Ohm's law. VRMS, of course, it is the same, so it is V maximum over rho 2, and this is Ohm's law, and so on, okay? So you can refer to this table in order to find V out and V out and I out and so on, okay? This is you can find it in the handout, okay? You can refer to it in order to calculate the V out and I out and so on, okay? Now, this is our, again, the same bridge rectifier. This is our AC supply. This is our rectification circuit, which is bridge rectifier, full wave bridge rectifier. And this is our load. Now, in this case, we have an inductor in series with the resistive load, okay? So V out is here, positive and negative, cross the load, cross the load. Load for us now is RL load, okay? RL load. Now, of course, the voltage will be the same. It is a full wave rectifier, okay? So it will be the same. This is one cycle, this is the second cycle. Now, what is interesting here, ya shabab, is the current. Can you see the current? The current in this waveform, it is a special current because of the inductive. Now, why is that? Can you see here, the current, it does not go to zero. It is continuous, and it is not going to zero. Now, this behavior of the current is caused by the inductive load. We know that the inductive is going to charge some current here, okay, through the positive cycle, and it will discharge. So it is going to charge in the positive cycle and discharge in the negative cycle, and so on, okay? So in this case, so this is charging of the inductive load, and it is discharging. So it is trying to keep up with the supply and try to smooth the inductor, the current, okay? So the inductor here is very important in order to smooth the current signal. If we use a huge inductive load, then the current here will be like straight line, which is the best DC output that we can get, okay? We know that the DC output should be a straight line, right? So in this case here, the current is smoother with the inductive load, and it is starting to see and to come like DC straight line. So we can conclude from the from this waveform is that we can use inductive load, more inductive load in order to smooth the current until we reach to straight line DC output current. Okay, before the current was going from zero and to the peak here and come back to the zero, so we have ripple here. Now we don't have we have less ripple, here. Okay, so يعني it is better with the inductive load. Of course, the inductive load is relative to the current, of course. Okay, and if we are going to smooth the voltage, we will use the capacitor, as you know, in order to smooth the signal of the voltage. Okay, inductive with the current because the inductive is charging the current, and for the capacitive load, the capacitor is a charging voltage. Okay. Now let's go to single phase full wave rectifier, uncontrolled rectifier using center tapped transformer. Now, in the center tap transformer, we have an issue with this connection. Now, let us see our connection here. Inshallah, we are going also to fix the problem here in the lab. Okay. So here we have a voltage supply, which is AC supply, right, through the primary winding of the transformer, and with the magnetic field induction, it will go through the winding, the secondary winding, and we have here D1, and here we have D2, and the center tap here is connected through the load. Okay, so this is our output voltage through the load. Output voltage is through the load. Now we can say that the lower peak diode voltage in the bridge rectifier makes it more suitable for high voltage applications. So in bridge rectifier, it is more suitable for high voltage applications. Center tap transformer rectifier, including the isolation, of course, we need to isolate from AC to DC. It is better to isolate between them, and this is an advantage. It has only one diode voltage drop between the source and the load. In the full wave bridge rectifier, we have 4 diodes, of course, right? And here make it desirable for low voltage, high current applications. Okay, because the voltage drop here is less, so we can use it for low voltage, high current applications. Now let me explain the waveform here. This is for the source voltage. We have an AC source, right? Cycle number 1, cycle number 2, and again the current, the same idea. Now for the output voltage, it is the same as the full wave rectifier. Why is that? Because in the positive cycle here, the current is going through the D1 and it will go through the load, right? This is for the first half cycle. For the second half cycle, this is the one. Okay, it will go through here through D2, and it will come back to the load. Okay, this is for the second half cycle, so it will be like this. Now the problem with the center tap, that the peak value or the output voltage, the average voltage, is half of the bridge rectifier. Now if we have a bridge rectifier, the output, let's say in the practical, we have done it in the practical, it is 90 volt, right, from the output voltage of the bridge rectifier. For the center tap, it is 45 volt. Okay, so it is half of the bridge rectifier. The bridge rectifier, as a conclusion, we can say that it is the best rectifier until now, because it has more output voltage, more output current, more output power, but of course it is expensive, not like the half wave rectifier and the center tap full wave rectifier. Now this is our example. This is the last thing in our lecture today. Now let us see this example. I think this example is in page, let me see. This example, you can find this example in the handout, okay, in the handout, and you can use equations, okay. This table, you can use this table, and it is in the handout, in the notes, in page 21, in page 21. Now let us analyze this circuit and we will see how can we solve, inshallah, the questions. Now consider the full wave uncontrolled rectifier circuit for the figure shown below. This is our full wave uncontrolled rectifier with a resistive load of 25 ohm. Okay, so we have a resistive load and it is 25 ohm, and our AC source is 110. Now if I did not mention anything here, shabab, it is RMS value, it is not the peak value, it is RMS value, it is not the maximum value, it is not V maximum, so we need to calculate V maximum. Okay, now for the frequency is 60 hertz. So let me just come back to this point. If I give you in the exam the AC source of 110 volts maximum voltage, then it is maximum. If I did not mention anything, it is RMS value. Now calculate the average value of the output voltage. If I say the average value, it means that V out, right? Okay, now V out, let me just take the iPad. Now V out يا شباب, we can find it here. Now this schedule, okay, is for the full wave rectifier. So you can refer to the schedule of full wave rectifier in order to find the V out average, okay? So as you can see, it is 2 V maximum divided by pi, okay? So A is, he needs to find V out DC, okay? And it is V out DC, so answer V out DC is equal to 2 V maximum divided by pi, right? Now V maximum, we have here, as I said, this is RMS value, right? And in order to find the V maximum, so V maximum, you remember this equation, shabab? V maximum is V RMS multiply root 2, right? So we can say 2 root 2 multiply V RMS divided by pi, which is 2 root 2 multiply 110 divided by pi, and the answer will be, you can use your calculator, shabab. The answer is 99.1 volt DC. Okay, so this is regarding A. Okay, this is A. Now I'm going to use another color for part B. For B, he said the average value of the output current. So he needs I out, right? I out DC. Answer, I out DC. From ohm 0, it is V out DC divided by R, and V out is 99.1 divided by 25, which is the resistance, and the answer is 3.9 ampere DC. Okay, now this is for B. Now let's go to C. See, he said the RMS value of the output voltage, the RMS value. So V RMS, V RMS. So V RMS, V out RMS. Okay, V out RMS. Now we can refer to this schedule again, and we can say this is our V RMS. It is V maximum divided by root 2. V maximum divided by root 2. Answer, V out RMS is equal to V maximum divided by root 2. V maximum is V RMS multiply root 2 divided by root 2. Okay, now of course this root 2 is going with this root 2, so it is 110 volt. Okay, which is DC. 100 volt, 110. Okay, now this is for part C. Now let's go to part D. We will use the blue color. So this is for T. Now he said the RMS value of the output current. We can use I out RMS. So he's asking about this, and answer I out RMS from ohms law, it is V out RMS divided by R, and it is here يا شباب. You can refer here, or we can use just only use ohms law. So it is 110 divided by 25, which is equal to 4.4 ampere DC. The last thing here يا شباب, last thing is E. Now in E, he said the average output voltage delivered to the load. So he is asking about P out. Okay, P out DC. Now how much the DC? Here is the P out DC. This is our P out DC, which is P out DC multiply I out DC. As simple as that. So answer, P out DC is equal to I out DC multiply V out DC. And I out DC is 3.9 multiply V out DC, which is 99.1. So it is equal to what? Equal to 392.3 watt. 0.3 watt. So this is how to solve the questions. In this lecture, we don't have a homework. Inshallah, you will see in the coming lectures more important topics, which is three-phase, inshallah, three-phase half-wave rectifier, uncontrolled rectifier, and also we will take the three-phase full-wave rectifier. I think to this topic, to the three-phase full-wave rectifier, inshallah, after that we will take our midterm exam. Let us see together, inshallah, what happens with the coming days, inshallah. Thank you so much for attending this lecture, and I hope you understand the topics today. And thank you, and stay safe.